This is the Orbital Congestion Report for the Women in Data Datathon 2025 and is brought to you by the Space Aware Trio. Here you can see the table of contents. Our team is made up of data analysts Veronica Polk, Shruti Bhaskaran, and Favor Adebayo. The challenge was to enhance space situational awareness using open data. The launch of thousands of satellites every year by governments, commercial companies, and private actors has led to increasing congestion of the Earth's orbital environment. This rapid growth, especially in low Earth orbit (LEO), poses rising risk of collisions, debris generation, and long-term sustainability challenges. We aim to identify altitude and inclination hotspots to assess if low Earth orbit (LEO) congestion is highly localized, especially around 550 kilometers. To achieve this, we will indicate where collision avoidance efforts or debris removal would have the most impact, reinforce that mega constellations dominate congestion patterns, show key stakeholders exactly where the traffic jams are. Key stakeholders are space agencies and regulators, satellite operators, SSA researchers, and space insurance companies.
Our project brings together three key datasets from the Unified Data Library, the LSATS data who gave us the orbital element, and Celestrak and SatCat who provided the classification. By merging them, we built a complete picture of satellites and debris in low Earth orbit. Methodologically, we acquired the data via APIs and text parsing, filtered for LEO objects below 2,000 kilometers, classified them into payloads, rocket bodies, and debris, analyzed distribution by altitude, inclination, and run, as well as identifying decay candidates. Finally, we visualize everything with heat maps, density plots, and growth trends. Collaboration tools like Teams, Python, Jupyter, and Canvas supported our analysis, documentation, and presentation. Our findings show debris isn't random. It's clustered between 700 to 1,000 kilometers, creating persistent debris belt. Meanwhile, Starlink and other constellations overlap with these zones, raising collision risk. The next slide shows where congestion in LEO is concentrated. On the left inclination cluster, Starlinks dominate at 53 degrees, while 97 to 99 degrees host sun-synchronous Earth observation satellites. On the right, altitude forms three hotspots: 500 to 600 km for Starlink, 700 to 1,000 km for legacy satellites and debris, and below 300 km where objects naturally decay. These overlaps create the highest risk of conjunction and collisions. Overall, about two-thirds of LEO's objects are active satellites, but 26% are debris and 6% rocket bodies. On the right, we can see that growth is accelerating. Active satellites nearly doubled from 2022 to 2024, and at this pace, we might exceed 45,000 by 2030. Without stronger mitigation, congestion and risk will only increase.
Our Orbital Congestion Report combines data from Unified Data Library and Satellite Catalog to identify altitude and inclination hotspots and assess orbital congestion in low Earth orbit. By classifying orbital bodies, detecting hotspots, and flagging decay risks, the tool provides decision makers with a clear view of where risks are most concentrated. According to our projections, LEO satellites may nearly triple by 2030. This rapid growth, combined with overlapping cells such as Starlink and debris at 500 to 600 kilometers, raises significant operational and ethical challenges. Recommendations and next steps. We recommend that operators strengthen collision avoidance practices and that policymakers enforce debris mitigation measures, including post-mission disposal. Additionally, Space Situational Awareness Organization should integrate multiple catalogs such as UDL and SatCat to build a more complete orbital picture. Our next steps include applying forecasting methods like ARIMA and PROPHET to project future congestion trends. This will enable proactive planning to keep orbital growth sustainable.
In conclusion, collision avoidance efforts or debris removal would have the most impact where debris overlaps with active constellations, thus reinforcing that mega constellations dominate congestion patterns as indicated in our findings. The Orbital Congestion Report is highly valuable to the future of space data, particularly in the mitigation of orbital collisions that pose great risk to orbital safety.